We've been working with a data set here that summarizes some calculators ACC has to lend to students. In this video, we're going to do some multiplication rule problems. So let's get started. Here in question number 1. What is the probability that on 3 draws without replacement you select 3 damaged calculators? First up, I just want to write this down as a probability statement. The probability on a first draw we get a damaged calculator, and then on another one we get a damaged calculator, and then on a third draw we get a damaged calculator. The multiplication rule says I calculate the probability of a damaged calculator. Alright, well we can go on and do that. I have 78 total calculators. We know that from a previous video where we added up all of the calculators in this table. If you haven't watched that video, or if you just haven't watched it in a while, you might want to pause the video here and make sure I'm not lying to you. But we do know there's 78 total calculators. Alright, now I just need to know how many of those calculators are damaged. Well, there are a total 11 damaged calculators. 2 and 3 make 5, 6 more is 11. Alright, well the next time through, I have to assume I've already drawn one damaged calculator. So there's 77 calculators because I've taken one out, I've drawn it, and there are only 10 of them that are damaged because I got a damaged calculator the first time. Next time through, I have to assume I've drawn 2 calculators, so there are only 76 total, and only 9 damaged ones remain because I've already drawn 2 damaged calculators. So to calculate this probability, I just need to multiply these 3 fractions. 11 out of 78 times 10 out of 77 times 9 out of 76. And I get a probability of about 0.002. That's the trick with the multiplication rule. I multiply the probabilities, but every time I calculate the next one, I have to assume I've already done the first thing. Alright, number 2. What is the probability that on 2 draws without replacement, that we get 2 TI-84s that are both in good working condition? So let's just say that's the probability of an 84 that's in the good category, and then we draw another 84 that's in the good category. Alright, so the first time through I have 78 total calculators. I need to know the total number that are both 84s and good at the same time. Well, there's 16 of those, right? Good category TI-84, 16 of those. Alright, but the next time through I assume I've drawn a calculator already, and I assume that it was a good 84, so there are only 15 left this time. Alright, so let's see. 16 out of 78 times 15 out of 77. I get a probability of 0.040 when I round to the nearest third decimal place. Question number 3 asks me what happens if I make 5 draws this time without replacement. What's the probability that on these 5 draws without replacement we get only calculators that are in the good working, that are in working order? So either good or okay, any of these calculators. So let's say that's the probability of working, and then another calculator that's working, and another one more, and one more after that. Using ampersands here to save some space, but working and working and working and working and working. 1, 2, 3, 4, 5 draws, 5 fractions. But every time I assume I've already drawn a calculator, so this number on the bottom goes down every time. So let's see, 1, 2, 3, 4, 5 draws. And on top, I need to know how many of the calculators are in either good or okay condition. So I need to add all these up. So let's see, they're 34 plus 18 plus 15. So to start, I had 67. But every time I assume I've already drawn one in that working condition. So these numbers go down by 1 as well. So I need to multiply those 3 fractions together, and we'll go from there. Making sure I actually managed to hit the right buttons on the calculator. Alright, and we get a probability of 0.457. Well, I have two more problems that I want to do on this problem set, but I'm going to go on and stop here and just start another video to finish things out.